about multi-way cut. So all of you probably know are aware of this problem ST cut. So you are given a weighted graph with two spatial vertices S and T, and you want to remove minimum weight set of edges or nodes. So if the weights are nodes, then you want to remove minimum weight set of nodes such that there is no path from S to T. So for example, this is the graph, then the set of green edges form a cut from S to T. We can find the minimum ST cut in polynomial time. So the multi-way cut problem can be seen as a generalization of this ST cut problem. In this, we are given again a weighted graph. Weights can be on edges or nodes. The graph can be directed or undirected. And we are given a special set of vertices which we call terminal, S1 to Sk. The goal is to remove minimum weight set of edges or nodes such that we disconnect all pair of vertices. Now this notion of disconnection is different for directed and undirected graph. So for example, if we have undirected graph with 4 terminals, we want to remove all paths from S1 to S2, S1 to S3, S1 to S4 and so on. Whereas if we have directed graph, then we want to remove paths from S1 to S2 and S2 to S1, S2 to S3 and S3 to S2 and so on. Now what is known about this? Okay, so we have either undirected or directed graph. The weights are on edges or nodes. So this leads to 4 different problems. The first one is edge weighted multi-way cut, which is the graph is undirected and the weights are on edges. For example, we have this graph. The weights are these 2, 1, 3 and so on. The set of green edges form a cut. So if we remove these green edges, S1, S2, S1, S3 and all the pair of terminals are disconnected. Then we can have weights on the nodes, so which we denote by node weighted multi-way cut. The graph is undirected and the weights are on set of nodes. So if we remove these green nodes, then all the terminal pairs are disconnected. Similarly, we can have directed multi-way cut. In this, the graph is directed and the weights are on edges. It's important that we have to cut both ways. So if we remove these green edges, all the terminal pairs are disconnected. So there is no path from S1 to S2 and no path from S2 to S3. It's important to cut both ways. It turns out that for the directed graph, the node weighted version is equivalent to the edge weighted version. So we don't need to consider the node weighted directed multi-way cut separately. So we have 3 different problems. One, edge weighted multi-way cut, which is undirected edge weighted multi-way cut, node weighted multi-way cut, which is undirected node weighted multi-way cut, and directed multi-way cut. So what is known about these problems? So for k equal to 2, the undirected multi-way cut is same as the ST cut. So we are given an undirected graph with 2 terminals S1 and S2, and we want to cut all paths from S1 to S2. Now this is same as the ST cut in undirected graph. And as soon as k gets to 3, the problem is known to be NP hard. Whereas for the directed graph, even with 2 terminals, the problem is NP hard. So note that this is not for 2 terminals, directed multi-way cut is not equivalent to ST cut. Because in ST cut, we have to remove paths going from S to T. So there is source and sink, and we don't want any path from S to T. Whereas in the multi-way cut problem, we are given 2 terminals S and T, and we have to cut paths from S to T and T to S. So we have to cut both ways. So the problem is different. Since it is NP hard, so we look for approximation algorithm. In this talk, we'll look at algorithms based on linear program. So let's say XE denotes whether an edge E is cut or not. So this LP formulation is for both directed and undirected graph. in the edge weighted case. So we have the constraint that, and Pij's are the path from Si to Sj. So for any path in Pij, that means for any path from Si to Sj, the constraint is that we have to choose at least one edge from that path. So the definition of multiway cut was remove edges such that there is no path from Si to Sj. That means for any path going from Si to Sj, we have to pick at least one edge. And the objective function is to minimize the weight of the edges we have chosen. And the dual of this problem is, the dual of this LP is the multi-commodity flow problem, flow LP. Is there any question till this point? All right. Similarly, we can have LP formulation for the node weighted case as well. In this case, we have one variable for each node indicating whether node V is cut or not. And again, the constraints are similar. For any path going from Si to Sj, the terminal Si to Sj, we have to pick at least one vertex so that we cut all paths. And the objective function is to minimize the weight of the vertices we have chosen. Sometimes we also refer to xv as the length of node V and xe as the length of edge E. We'll see why we do this. Okay, so what is known about this LP formulation? It is known that for the undirected edge-weighted multiway cut case, the integrality gap is exactly 2 times 1 minus 1 over k. There is also a different LP formulation which gives better than 2 approximation for the undirected case. We are not going to discuss that in this talk. The current best approximation, the current best integrality gap known for that LP is 1.2965. The lower bound is not this. It is also known that the edge-weighted multiway cut in the undirected graph is APX hard to approximate. So what is known about the node-weighted multiway cut and the directed case? So Garg, Vazirani and Yanakakis in 94 proved that the node-weighted multiway cut case in the undirected graph, they gave 2 times 1 minus 1 over k approximation. They proved that the LP we saw earlier for the node-weighted case is half integral, so which gives 2 approximation. With one trick, we can improve that that by a factor of 1 by k. And they also reduce vertex cover to node-weighted multiway cut in approximation preserving fashion. So this problem, node-weighted multiway cut, is at least as hard as vertex cover. Under unique games conjecture, vertex cover is hard to approximate better than 2. So 2 approximation is the best we can hope for node-weighted multiway cut if we assume unique games conjecture. Now note that this rounding assumes that we know the optimal solution of the LP. Now computing an optimal solution can be computationally expensive, whereas if computing an approximate solution of the LP is relatively faster. So we can find 1 plus epsilon approximation of the LP in significantly faster time. So the question is, can we round any feasible solution? That means, so for the LP, if we are given any feasible solution, by feasible I mean just the vector x which satisfies the constraint. Sorry.
The answer is yes. I have this in mind.
Oh. Oh. Okay.
For node weight.
All right. I was not.
With ratio of 2 versus 2 times 1 plus x.
Oh, okay. All right. Okay, it's already known. I was not aware of this. Okay. Okay, so we also give one rounding scheme for this. So the case of directed is more involved. So in 97, Naur and Zosin gave a 2 approximation for the directed multiway cut case. The LP formulation is not the LP formulation we saw earlier, the standard distance-based LP formulation that each path from Si to Sj we choose at least one edge, or the length of that path is at least one. They consider a different LP formulation which they call relaxed multi-commodity flow. And they also have to round the solution optimally. And so this LP, the cost of this LP is within a factor of 2 of the original LP, and they round this LP without any loss. So this indirectly shows that the standard LP formulation we saw earlier has integrality gap at most 2. Now again, this computing the optimal solution can be expensive. Also, we would like a direct proof of the integrality gap of the LP. So we get the same approximation factor, so we don't improve the constant because under Unigame's conjecture, this is the factor 2 is the best. We might and our algorithm requires any feasible solution. So if we have 1 plus epsilon approximation of the LP, we get 2 times 1 minus 1 over k times 1 plus epsilon approximation. For the directed case also, we get 2 approximation. The algorithm is based on the standard LP formulation we saw earlier, and again it requires just a feasible solution. So we can work with the 1 plus epsilon approximation of the LP to get 2 times 1 plus epsilon approximation. Additionally, we also prove that the integrality gap, so for the node weighted case, the integrality gap was exactly 2 times 1 minus 1 over k. It is easy to prove that node weighted multiway cut reduces to directed multiway cut. So the directed multiway cut has integrality gap at least 2 for arbitrary k. We prove that even with just 2 terminals, the integrality gap for directed multiway cut is 2. And our instance is planar. So even with planar graph, directed multiway cut has integrality gap 2 for just 2 terminals. In this talk, we'll look at this part, 2 approximation for the directed multiway cut. So let's remember the LP again. We have, this is not indented properly, sorry. For each path from Si to Sj, the length of that path, so Xc are the length of this path is at least 1. And the objective function is to minimize the weight of the edges chosen. So first we do one reduction step. Let's say we have just 3 terminals, S1, S2, S3. We add 3 new vertices, T1, T2, and T3. From T1, we add edges to S2 and S3 with length 0. From T2, we add edges to S1 and S3 with length 0. And from T3 to S1 and S2. If we have more than 3 terminals, so let's say we have S1 to Sk, we'll add k new terminals, T1 to Tk, and Ti will have edges to all the terminals except Si of length 0.
Of weight.
So Xc are the length, no, length is 0, weights are infinite.
Weight as length 0.
Yeah. Okay, let's say DUV denote the shortest path. DUV denote the shortest path length from vertex U to vertex V with this length Xc. Note that if we have any feasible solution of the LP and we add this k vertices later with these edges, the LP solution will guarantee us that the distance from Ti to Si is at least 1. So for example, distance from T1 to S1 is at least 1. Why? Because any path from T1 has to either go through S2, and the distance from S2 to S1 is at least 1 by the LP, or it has to go through S3, and the distance from T1 to S3 to S1 is at least 1. So this gives that the distance from Ti to Si is at least 1. And now the goal is to remove all paths. So the equivalent to multiway cut, equivalent to disconnecting all Si, Sj is disconnecting all paths from Ti to Si, and under the assumption that we don't remove these new edges we have added. So the reduction step was add new vertices T1 to Tk, and for every I not equal to j, add edge Ti Sj. So from T1 we add edges to S2, S3. From T2 we add edges to S1, S3, and so on. The rounding algorithm is fairly simple. So we pick theta, number theta from 0 to 1 uniformly at random. We consider the theta radius ball around Ti. So we look at all the vertices u in V such that the distance from Ti to u is at most theta. So, and we look at the set of edges which are going out of this ball of radius theta. So the formal definition of this edge boundary is edge boundary of a set S is all those edges uv such that u is in the set and v is outside. So note that these edges are directed. So the starting point of the edge should be or the tail of the edge should be inside the set and the head is outside. So the rounding algorithm is pick theta in 0, 1, look at theta radius ball around each of the Ti, and look at the outer edge boundary of this set and return the union of these sets. So note that since we choose theta in 0, 1, we don't cut the new edges we added. So the distance from T1 to S2 is 0. Since we are choosing theta from 0 to 1, it's strictly greater than 0. We never cut the new edges. So for example, if this was the graph, we look at theta radius ball around T1 and we remove the edges going out. Similarly, we remove the edges going out of T2 and so on. Note that in this case, the balls of radius theta around Ti's may intersect. So the analysis is a bit subtle because we have to calculate the probability of the union. We can't calculate the probability that any edge is in one of the edge boundary and take a union of those take the union bound. So we'll see what the analysis. It's actually short. Any question about the algorithm so far? Okay. So let's assume there is some edge uv. When is this edge uv is in the edge boundary of the theta radius ball around Ti? This is sort of the case when u is inside the theta radius ball and v is outside. This happens when theta is greater than the distance from Ti to u. So theta is greater than the distance from Ti to u, and theta is less than the distance from Ti to v. So u must be inside and v must be outside. So theta must be in this range. By triangle inequality, the distance function satisfies the triangle inequality. So the distance from Ti to v is at most distance from Ti to u plus this length xe. So E is this edge uv. So theta must lie in this range if edge uv is cut by theta radius ball around Ti. So probability that an edge E is in the final cut is less than equal to the probability that theta is in this union of this range. Okay, so let's assume, so consider the distance from S1 to U, S2 to U, and so on. So rename the terminal such that the distance from S1 to U is smaller than distance from S2 to U, and so on. So note that, so here we are considering distance from the original terminals S1, S2 to U. So note that we constructed the new graph by adding T1, T2, T3 such that T1 had 0 length edges, edge to S2 and S3. T2 has 0 length edge to S1 and S3, and so on. Okay, first claim is that distance from T1 to U is equal to the distance from S2 to U. Now, why is this true? So T1 has to go through either S2 or S3. Now, S2 is closer to U than S3. So the shortest path from T1 to U will be through S2. So the distance from T1 to U is equal to this. So the interval I1 is T1U is equal to distance from T2 to U, and so the interval I1 is this. Now the critical thing is that all the other distances are equal. So for example, consider T2. So T2, any path from T2 to U has to either go through S1 or S3. Since S1 is closer to U, the distance from T2 to U is equal to, so distance from T2 to U is equal to the distance from S1 to U. Similarly, T3 has to, the path from T3 to U has to go through either S1 or S2. So the distance from T3 to U is also equal to the distance from S1 to U. Similarly, T4 also has an edge. So in this picture we don't have T4, but in general so in general note that we add new vertices T1 to Tk, and for each, so for example, if we had T4 will have edges to S1, S3, S1, S2 and S3 with length 0. So T4 has to either go through S1, S2 or S3, S5 and so on. Since S1 is closest, distance from T3 to U is also equal to distance from S1 to U. So since distance from T2 to U is equal to distance from T3 to U and so on, all these intervals are identical. So all these intervals are equivalent to this. So since the probability that edge E was in this cut is less than the probability that theta is in this interval, union of these intervals. Union of these intervals are union of these two intervals. So I1 is this, and all the other intervals are this. So the union of all these k intervals are union of this interval and this interval. Since theta is chosen uniformly at random between 0 and 1, probability that theta lies in one of these two intervals is the sum of length of these two intervals. Note that each interval has length at most xc. So probability that theta lies in one of these two intervals is at most 2xc. Now using the linearity of expectation, expected cost of the solution returned by this is at most twice xcwe, which is the LP cost, and we can actually de-randomize this algorithm very fast, and we'll get almost linear time algorithm. So given a feasible solution of the LP, in almost linear time we can find a cut with cost at most twice the solution, the fractional solution cost.
Do you expect
Yeah, we can, that's what I said. We can de-randomize this algorithm in almost linear time. Now, there is one very interesting case of directed multiway cut with just two terminals. So we have two terminals, let's say we call them S and T. We want to remove all paths from S to T and T to S. Now there is a trivial 2 approximation, how we can first solve ST cut and then we can solve TS cut. The question is, can we do better than this? So with this simple problem, just two terminals, cut from S to T and T to S, can we do better than 2 approximation? We proved that the integrality gap of the LP we saw earlier, even for this case, is 2. So by that LP we cannot do better. So the open question is it hard to approximate better than 2? Thank you.
Any questions for Vivek?
Yep.
Is there a natural LP which is considered for the stronger or like immediately stronger?
For the directed case, I don't think so.
One other comment, I mean, this is the same rounding